Hi everyone, let's talk about string theory a little bit. So we're at this point where we've got the standard model of particle physics, extremely successful, and we're trying to push beyond it to find some overarching framework that explains all of the phenomena of nature, including gravity, which is fundamentally described by the general theory of relativity. So folding these together is a huge theoretical problem, hasn't been cracked yet. We talked about supersymmetry in the last video, which is really focused on, some kind of coincidences and clues in the standard model itself. I call string theory kind of a Hail Mary approach, where supersymmetry doesn't really talk about gravity per se, whereas string theory does. String theory just tries to go for the whole ball of wax in one shot. And basically the way this works is that if you step back and look at Einstein's theory of general relativity, in the 50s or 40s and 50s, when Einstein was working on a theory beyond general theory, now the standard model, remember, the standard model is 20 years in the future at this point. So Einstein's working with general theory of relativity, and one crazy fact is that if you take this general theory of relativity, which teaches us to think beyond the three dimensions of space, incorporate a fourth dimension, which we call time, if you take one more step and add a fifth dimension, talk about the 5 dimensions of this, whatever you want to call it, Maxwell's equations pop out of that theory almost for free. And so a 5-dimensional general theory of relativity has electromagnetism baked into it in some sort of way. Now, this is an intriguing theory and somehow speaks to some sort of unity between gravity and electromagnetism. Einstein worked on it for essentially the last decade of his life, never really got anywhere with it. So that idea has kind of just sat on the physicist's bookshelf, kind of unutilized. So then you kind of move through history, 20 years, you get the standard model. What happens is that physicists in the 80s discovered that if we, instead of 5 dimensions, talk about a 10-dimensional space, a 10-dimensional space, somehow, and we start thinking instead of particles, we talk about rings, strings that vibrate in this 10-dimensional space, that somehow the mathematics produces a theory that has both general relativity and features of quantum field theory in it. Now, kind of in a rough way, you imagine, this is kind of a rubric for the Feynman diagram, right? You've got an interaction. Basically, the lines are representing fundamental particles. Well, in string theory, instead of particles, you imagine these strings. And so this interaction is not a tree picture here, but more kind of this 2-dimensional sheet. And the important thing about string theory is that this is a real problem for quantum field theory. Essentially this interaction occurs at a single mathematical point in space. That creates a lot of infinities and issues, kind of effectively dividing by 0 type issues for the theory, which is why it took 20 years beyond Dirac's theory of the electron in 1927 to create a quantum electrodynamics theory in the 50s. The nice thing about string theory is it avoids that issue. And so by doing this, you get a theory that's a little bit more satisfying. Also, this is a problem for quantum, or for the quantum field of gravity, because this high energy density requires some sort of roll-in of gravity. Now, the extra dimensions are used to explain why we don't really see strings at a fundamental level. The strings are vibrating in non-spatial dimensions. You've got 4 space-time dimensions. You've got 6 other dimensions where these strings can vibrate. Now, I know this kind of doesn't make sense kind of doesn't make sense to me either. But that extra freedom, those extra degrees of freedom of vibration, can mathematically generate a theory that looks like the general theory of relativity as well. Now, there are kind of like 4 or 5 different variations on a theme for string theory. In the 90s, people rolled this together into one massive theory called M-brane theory, where it's not 10 dimensions but 11 dimensions. There's also a 26-dimensional theory. The issue with all of these string theories is that they're all completely made up. As I've mentioned multiple times, the standard model is sufficient. We don't have any piece of evidence to justify whether we want to talk about this string theory or that string theory or supersymmetry or something altogether different. It's a fundamental issue, and it's one of the reasons why physicists are interested in creating larger and larger atom smashers. The reality is that's very expensive, and to get to the energy levels we're talking about, probably are not even possible on the surface of the Earth. We'd have to be looking at astronomical distances. Even clues from the Big Bang can be used to generate evidence or clues for this kind of frontier of physicists. But all of this is speculation, and it's interesting, but fundamentally doesn't move the ball along unless we can actually show something with the mathematics. And that's one of the fundamental problems with all of these string theories, is that the mathematics is so freaking complicated that to generate a single experimental prediction is nearly impossible. And so not only do you have a theory which doesn't have any kind of unique experimental basis, you almost have a theory that's unusable in principle, in practice, right? And so I'll be interested to see where this goes in the future.